All right. Well, good morning, everyone, and welcome to our first Monday morning lecture here. My name is Michael Mueller. I'm a professor in the Department of Mechanical and Aerospace Engineering, and so it's my pleasure to welcome you to Princeton in a much more formal way than having a 2-year-old crawl up the stairs while I attempted to welcome you yesterday. So it's my distinct privilege to introduce this morning's lecture, Professor Rich Yetter, Star 85. So just to give you some context, at Princeton, alumni are introduced with their letter of graduation. If you're a graduate alum, you have a star. So PhD from Princeton 1985. So Rich Yetter, Star 85. Professor Yetter is a professor at Penn State University. His expertise is largely on energetic materials, which of course is the topic of his course today, tomorrow, and Wednesday. And it really is a rich phenomena of many interacting pieces of physics, and there's no question that he's the world's leader on this topic. So you're truly in for a treat here as well. And so just to say a couple of other words about Professor Yetter, a mark of a great faculty member is the people that they mentor, and so actually one of my PhD students actually did some work with Professor Yetter, and he's doing great so far. So far, so good there as well. And then Rich is also very generous with his time. He's the editor-in-chief of Combustion Science and Technology, which is a thankless job because no one ever thanks you, and if your paper gets rejected, you get yelled at. So it really is something that takes a true servant's heart to take care of. And so without further ado, I'll turn it over to Professor Yetter.
Thank you very much, Mike. It's a great pleasure for me to be back at Princeton. I left Princeton in 1999. After my PhD, I stayed on as a research scientist and lecturer for close to another 20 years. And then I've been at Penn State since as a professor. And I'll give you a little bit more history of myself. Obviously, before I came to Princeton, I worked in the Ford Research Labs on IC engines. And there I recognized, having a master's from Cornell, where I did gas turbine type work, I did a lot of fluid mechanics. And one of the things I was missing when I was at Ford was a little bit of the chemistry aspects of combustion. And so I came to Princeton to learn a little bit more about that. And that sort of got me into looking at energetic materials, which is a very diverse subject, including chemistry, fluid mechanics, and also material aspects, you'll see. I mean, the composition of different solids and the way you fabricate them is very important to how they burn and combust. So today, what I want to do is I put together a series of notes, and the notes I put together is probably too many to cover in a 3-hour course. And so I may shoot around a little bit within them, and you'll even notice I did put an appendix that talks a little bit about rocket propulsion and particle combustion if you haven't had a combustion course. So for the group in the audience, how many people have had a combustion course of some sort? Okay, so you've got a good background in terms of fundamental combustion, because I treat, energetic materials as a type of course that many students won't see initially, even as a graduate student right away. And so it's sort of a unique topic. And in fact, I don't teach a particular course on energetic materials at Penn State. So I've sort of developed this course in particular for the summer courses that are given here. Okay, so it's a flexible course. If you have questions at any time, please, stop me, interrupt me, and I'll try to answer those questions. So here's sort of an outline which is given in the notes. And you'll again see that I'm trying to cover quite a bit of material that basically initially concentrates on solid propellants or solid energetic materials. And then I move on to basically particle combustion. This would be looking at metal combustion and then the integration of those metals and composite materials and how that affects their burning process. And then later, I look at some of the other directions in which applications of energetic materials are being used. One of the interest subjects there that became popular a few years ago was energetic materials have a high energy density. So the question is, how can they replace electrochemical batteries? So if I'm looking at electronic chips, can I actually put an energetic material on an electronic chip as basically a source of energy that would fire up a sensor, that would make the sensor jump and do different type of things? And that's one of the sort of niche areas in which you'll see energetic materials being applied. Okay, so the first thing I want to do is sort of give a background in energetic materials, and starting off with a little bit of probably nomenclature, definitions, and things like that, just to get us all familiar with the subject if you're not familiar with it. As Mike mentioned, I'm now at Penn State. If you don't know where Penn State is, it's right in the middle of the state of Pennsylvania, in a town called State College. The university itself is in a location called University Park. It's about a 3.5-hour drive here to Princeton University. I have run a number of research laboratories at Penn State, and I'll give you an overview of those laboratories right here. The first one I actually moved into after I left Princeton was a building called PERC at the time. It's now just Research East. I have a number of fundamental laboratories there where I do benchtop experiments, say on optical benches. And in those experiments, I don't need to worry about hazards. Okay, energetic materials, if you obviously confine them, can create hazardous in terms of overpressurization. And as a consequence of that, I now operate what's referred to as the high-pressure combustion laboratory. This laboratory was actually initially developed by Professor Ken Kuo, who also got his PhD at Princeton, working for Martin Summerfield, another well-recognized name in the field of energetic materials. Martin himself worked for Theodore von Karman out at Caltech. And so there's a long history of of energetic materials running through Princeton University. In the high-pressure combustion laboratory, we have about 10 reinforced cells. So these are very thick reinforced concrete walls in which the experiment's conducted obviously in the cell, and the operator runs outside of the cell the experiment, so there's no chance of a hazard. The other laboratory that I now operate is the cryogenics combustion laboratory, in which we have the capability of actually running cryogenic, for example, cryogenic oxygen, if we were looking at bipropellant rocket motors. Outside of these laboratories, we have an outdoor test facility in which we can run rather large rocket motors. It's just a concrete wall with an iron mesh above the ceiling. And at the exit right here, there's basically a stone wall in case there was a rupture of the nozzle or something like that. Everything would fly into the stone wall itself. Now we deal with energetic materials, so those energetic materials have to be stored properly, and we have a series of magazines, a 1.3 class magazine, and you cannot see it on this, but some distance away, a 1.3 class magazine. So I'll give you a little bit more of my history. As I said, I started out looking at gas turbines, went to Ford Motor Company, studied IC engines, came to Princeton University, learned more about chemistry, and as I started leaving Princeton, moving to Penn State, I moved into the field of basically propulsion and rocket propulsion in particular. Okay, so what are energetic materials and how can they be classified? Well, you can classify them as explosives, propellants, or pyrotechnics. If I look at those materials, one of the thing that's common among all of them, you do not need a separate oxidizer, so the oxidizer and fuel are carried together. Okay, they're very sensitive reactions to temperature and have a very high energy release. If I look at the three different materials, the ingredients that go across them can be very common. It's just how they're formulated with other materials and how they're basically ignited. Okay, some applications, and this is just a short list of applications. Blasting explosives for mining, tunneling, demolition, and weaponry, explosive bolts and actuators, propellants for rockets and guns, gas generators for fire extinguishers or for airbag inflators. In the case of an airbag inflator, one wants to rapidly produce a large amount of gas to inflate a nylon or polyester bag in about 15 milliseconds. So there you've got velocities on the order of 100 meters per second. Light generators or sparklers for fireworks or for rescue signals, including underwater signals that produce a bright light, yellow-white hot emission at, say, greater than 1500 Kelvin, and colored shimmering sparks. Also smoke generators for rescue signals, military purposes, smoke grenades, noise generators for fireworks, for rescue signals, stun grenades. Combustion synthesis is actually related to energetic materials. If I'm looking at it from a solid point of view, not necessarily combustion synthesis through gas phase flames, but if I'm trying to produce a unique material through, say, a condensed phase reaction. Microthrusters, microactuators, micropyrotechniques, chemical storage for hydrogen. One of the unique aspects today is how can I store hydrogen efficiently and produce it on the fly? Well, in many cases, you can do that through combustion of a condensed phase energetic material that's highly loaded in hydrogen that produces hydrogen. Emergency airplane crew and passenger escape systems. So these are all examples, and there's many more. I always like to give a little bit of a history of energetic materials and combustion aspects in general. And many of you might know these characteristics, but it's fun to go back and look at some of them. Black powder was a discovery at the end of the first millennium, potentially a Chinese alchemist who may have been experimenting with various flame-producing materials. These studies typically involve mixing and heating of various substances, including sulfur, charcoal, and eventually saltpeter, which is potassium nitrate, KNO3. And depending upon the proportions of those particular three ingredients, one could get explosive or propelling properties, which were applied to various pyrotechnic devices, including fireworks and rockets, called fire arrows. So in addition to the proportions, another important property is basically their density. How compact and pressed, how much voids do I have in the material itself? If I have a lot of voids, then I can actually propagate the flame very quickly through those voids and get a very fast combustion reaction, whereas if it's very dense material, it's only going to burn on the surface. And then from China, the knowledge spread to India, to the Arab countries, and eventually Europe. So a couple of the very early people involved in this was Roger Bacon, who brought the knowledge of black powder to Europe. He was an English philosopher and Franciscan friar. He was probably one of the first people that started to looking at a modern methodology approach to science. And so he basically believed in the study of nature through empiricism. And in the late 1240s, he wrote basically Opus Majus, which was something that was given to the Pope at the time, where he actually described the idea of black powder without writing the correct formula. And he kept the actual formulas as a secret at the time. And then Albertus Magnus, who lived about the same time, was a German Dominican friar and a Catholic bishop. He wrote a series of books on what was referred to as on the wonders of the world that was very popular, even you can find them today. And in this series of books, he actually described many formulations of black powder, those that would burn fast, those that would burn slow. He actually reported that if I have 4 parts saltpeter or potassium nitrate, 1 part charcoal, and 1 part sulfur, I'd get a very explosive reaction. And then he acknowledges basically spreading the knowledge of black powder across Europe. Now, from 1200 on until about the 1800s, black powder was the common method of basically using a condensed phase energetic material. And you can look at, it was used in weaponry, it was used for fireworks and things like that for years. And in fact, if you look at it in the US, Francis Scott Key wrote, "From the rocket's red glare during the War of 1812 between the American colonies and the British colonies." And that what he was referring to with the rocket's red glare was a British rocket that was referred to as the concave rocket based on black powder. And as I said, then there had been experiments on new powder formulations since the beginning of the 19th century without much success and with a lot of accidents because, again, of the porosity of the black powder and how well you packed it and things like that. And also, the elimination of smoke and solid residues wasn't necessary for many practical applications. So the first breakthrough in making a smokeless powder came in France in 1886 by Paul Vier, who found ways to nitrate cotton so that it was possible to dissolve in solvents, which led to basically gelatinized masses of nitrocellulose. So cellulose is obviously just wood, and the idea of, which is a granular fiber-type material, and nitrating it basically added NO2 groups to it to make it an energetic material, which then could be formed into grains. And the word grains basically is a form of a propellant in its shape. Then a propellant grain would be what you would put in a rocket motor, for example, and it could have different shapes. Now you also see later on, Paul Vier is credited with how fast energetic materials burn. And there's a law that's referred to as the burning rate law that says the burning rate is equal to some proportionality constant, say A, the pressure to some exponent N, okay? And that's either referred to as St. Robert's law or Vier's law, okay? And it was at first initially found empirically, but later derived theoretically. Okay, then it comes along the Noble family and Alfred Noble in particular. The family business was basically the production of nitroglycerin. Nitroglycerin is a liquid versus the nitrocellulose, which is a solid. Very sensitive material, the liquid. They had a factory that was destroyed in 1864. They developed the fulminate detonator, developed dynamite and blasting gelatin. In 1887, Noble patent balistite, which is based on nitrocellulose plasticized with nitroglycerin. Okay, so the idea here was if I have this solid nitrocellulose and I add to it nitroglycerin, which is a liquid, the nitrocellulose will dissolve in the solution, become a gel, and I can start forming that into different types of grains. And as I note here at the bottom, it was the first step then in the direction of what's now referred to as an extruded double base energetic material. And then if I look at the other type of energetic material used in propellants, it's referred to as a composite propellant. So as I note here, composite propellants are the base of all modern developments of solid rocket propulsion systems. And in 1942, John Parsons, who worked with Theodore von Karman out at Caltech, invented the first cast composite propellant. While watching tar paper being applied to the roof of a building, he realized that asphalt mixed with the right solid oxidizer could make a good solid propellant. It could be easily poured and formed when hot, and when it cools and dries, it would do that without brittleness and without cracking that basically plagued the use of black powder mixtures. And so they're the basically early developments of what are now referred to as a homogeneous propellant and a heterogeneous propellant. Okay, again, let's take a look at some power densities to give you an idea how much energetics are in these materials. If I have a acetylene air flame, I'm producing about 100 watts per centimeter cubed. If I look at the deflagration of an energetic material, for example, a gun propellant, I'm producing about 10 to the 6 watts per centimeter cubed. And if I detonate a high explosive, I have about 10 to the 10th watts per centimeter cubed. If I look at energy of energetic materials, I put sort of a hierarchical chart here, starting at the bottom, going to higher energy densities. The bottom one is TNT, which is trinitrotoluene, has an energy of about 7.6 kilojoules per cc. LX17 is triamino trinitrobenzene, which is this TATB that's mixed with something called CalF, which is just a fluoropolymer. C4 is based on what's referred to as RDX, Royal Daughters Explosive. I'll show you these formulas later. That's mixed with a binder and a plasticizer. And then neat, triamino trinitrobenzene. LX14 has a very high loading of HMX, which is Her Majesty's explosive, has on the order of like 95% with S-stain and a binder mixed with it, which is a high explosive. HMX itself, tritonol is TNT mixed with aluminum. And then Cl20 is an organic material like HMX and RDX. It's one of the most energetic, just pure, neat organic materials. And then there's different combinations of materials, and the highest one I have listed here is ammonia dinitramine that's mixed with aluminum. But you can see one can have a very large range of energy densities in these materials. Okay, so give you a brief introduction of some of the structures in some of the materials I just named for you. The first I want to look at monomolecular energetic materials, which have the oxygen and the fuel basically bound together molecularly. And so I give an example here of Her Majesty's explosive HMX. And you can see it's basically a ring structure with singly bonded nitrogen and carbon in the ring. Off of each of the nitrogen atoms, I have nitro groups, NO2 groups that store the oxygen. And off of each of the carbon groups, I have 2 hydrogen atoms, okay? And I show then below that I can either run this in a deflagration mode, which is basically a subsonic mode of like a premixed flame, and it's very sensitive to pressure. So if I move from left to right here, going to higher pressures, this is a piece of RDX here that's burning, say, near atmospheric pressure, and you can see the flame forms a stage that looks like this. So you're getting some deep composition. Then the flame's located here, one of the stages, and then I go on to a second stage. As I start to increase the pressure, this stage of the reaction moves closer to the surface, and by the time I get to higher pressures, that stage can move right on the surface. And depending on how I ignite it, I can either deflagrate it or basically detonate the material. What are plastic bonded explosives? They're basically developed on a similar chemical process as those for composite rocket propellants. It's basically taken crystalline materials such as HMX and RDX, which are basically your oxidizers, that are mixed with liquid copolymers such as polystyrene and polybutadiene prepolymers that are then cross-linked in a polymerization process, and then cured to create a solid. Okay, and I show an example here of PBX 9501, which has 95% HMX, 2.5% S-stain, and 2.5% BDNPA. And here is basically a micrograph of what that material might look like. Okay, so you can see it just looks like a highly loaded particle material with very little binder holding the particles together. These are examples of basically the HMX crystals all throughout it, and you can see there's basically a particle size distribution. Now, today, just to give you an idea of explosives, I just pulled out some quick examples, but one of the biggest industrial disasters that's still in the US is the Texas City disaster in 1947 of ammonium nitrate. Ammonium nitrate is basically your fertilizer, and this happened basically on a ship from France that was highly loaded in bringing basically ammonium nitrate to the US. Before it was unloaded, there was a fire in an adjacent ship. That fire spread to the ship from France. The basically ship first exploded and then detonated. I don't have much of it here. You'll see the first explosion. Okay, so given a quick example and describing some propellants next, I can have liquid, hybrid, or solid propellants. In the case of liquids, I can have monopropellants. Some examples there are nitromethane. So nitromethane would be where I take methane and I take one of the hydrogens that is on methane and I displace it and add an NO2 group. Okay, so that becomes nitromethane. And you can go up the alkane series and do it for all of those. So I can have nitropropane, etc. A hydrazine is typically a very common monopropellant today. Toxic, very hazardous, and one of the big efforts throughout the space community today is to basically replace hydrazine with something else. Okay, that's less toxic, and one of those examples of a replacement material is referred to as hydroxylammonium nitrate, in which it's dissolvable. This is a crystalline oxidizer that's dissolvable in water to very high concentrations. It's basically highly loaded in oxygen, and then to that mixture I can add a fuel, and I can change sort of the fuel to oxidizer ratio of that particular propellant. And you'll see all across the internationally, different countries are looking at HAN. Japan has its own version of formulation. The US has its own form of formulation. And in Europe, basically looking at different newer oxidizers, such as HNF and ADN. One can have bipropellants. Here I just say liquid hydrogen and liquid oxygen. But these can also be hydrazine and say NTO, nitrogen tetroxide. A hybrid rocket system obviously has one of the fuels or oxidizer as a solid and the other as a liquid or a gas. So here I have a solid fuel, which would be hydroxyl terminated polybutadiene, and my oxidizer then would be liquid oxygen. In the case of solids, I can classify them as either a homogeneous or a composite material. In the case of homogeneous, I can have a single base, which would be nitrocellulose. I can have what's referred to as a double base now, where I mix the nitroglycerin with the nitrocellulose. And I can even have something, say, would be a triple base, where I might add a high explosive, such as RDX with the NCNG. In the case of composites, some examples might be ammonia perchlorate, which is a crystalline oxidizer, has a high concentration of oxygen that when it decomposes, it releases oxygen, about 23% by volume. that can react then with a solid fuel, hydroxyl terminated polybutadiene. And to that mixture, I can add additional fuel, which would be aluminum, or I could add additional oxidizer, which would be, say, some high explosives, RDX or HMX. So there's a whole variety of looking at different formulations. I show an example here. This is in our outdoor test facility. And here we were burning basically ammonia perchlorate, hydroxyl terminated polybutadiene, propellants with and without aluminum particles. And the focus of this project was not basically the burning of the propellant itself, but how that propellant affected nozzle erosion. Okay, so if I'm looking at some sort of device, missile or something like that, the erosion of the nozzle becomes very important because it changes the cross-sectional area at the throat, which is very important in terms of determining the thrust and then the range and things like that. So what we were tasked to do was basically set up a very simple experiment where we could record the rate of erosion of the nozzle and provide that data to NASA so that they could check out their models in a simple geometry. So this is a simple two-dimensional geometry of a nozzle that you see in the upper right. It's a carbon composite nozzle here. And what you're going to see then is the ignition of the motor. Much of this that you're seeing in the bottom is basically water, steam that we added to the exhaust to basically cool down the exhaust. But what I wanted, and I'll play it again, what I wanted you to see in this upper right corner was we did X-ray measurements. So the windows here are basically on this motor are made out of aluminum. And we did X-ray measurements to get instantaneous regression rates of the nozzle itself. And if you look at the end here, I'll show you what happened. This black line that was here was the original location of the nozzle. And then as the gases went through it from left to right, they started to erode the nozzle. And now you can see two different other lines. There's this fuzzy line here, and there's a green line here. Okay. Below the green line is the virgin material. Above the green line is basically the material in this carbon composite material where the binder started to burn out. And this material here has become very porous. And so that's a good factor, because if it's very porous, the thermal conductivity goes down. And so the heat that's going into the subsurface, the virgin material, is reduced. So I reduce the erosion rate. And to a certain degree, I maintain part of the geometry out here to basically guide the flow through the nozzle. Okay, so I'll play that one more time if you want to look up in that right-hand corner. As I said, NASA then took that data and confirmed their models. Okay, what are pyrotechniques? Often used as fireworks of various kinds. These include what are referred to as thermite or redox reactions, where I take maybe a metal and a metal oxide. And my example here is aluminum with iron oxide. And thermodynamically, when I mix those two and I bring it to a high enough temperature to ignite those particles, the oxygen on the iron oxide wants to move to the aluminum to create aluminum oxide, and I'm left with pure iron. Okay, that releases a lot of energy. Okay, and people use those type of reactions then in synthesis reactions to create different types of oxide materials as a final product. Another example in the same frame of light is intermetallic reactions, where I take two metals and say in particulate form. And my example here is aluminum nickel. Again, when I bring those to a high enough temperature, they'll form a metal alloy, some aluminum nickel alloy, and again, releases a significant amount of energy. Now, obviously, when they react, they can form temporary, some gas, but by the time they start to cool down, the final products are in the condensed phase. Pyrotechniques have been used as igniters, incendiaries, and other means themselves. Now, I also note here the word pyrotechniques, if I look at it internationally, is often used in the same frame as the word energetic materials is used. So here's an example of a thermite reaction. This is based on particles that are on the size of microns, tens of microns in size, so the particles are relatively large. And what I have here is just basically a vase. And inside the vase then is aluminum particles and iron oxide particles. When I bring the material to a high enough temperature to ignite it, I'll basically get a reaction. And you can see it's hot enough basically to create liquid alumina, which means I've got to be at a really high temperature because its melting point is probably around 2300 Kelvin. Okay, so again, some more definitions kind of to move through this material. A solid propellant is a solid state substance which contains both oxidizer and fuel and is able to burn in the absence of ambient air. Solid propellants usually generate a large number of gaseous molecules at high temperatures. We're looking at temperatures between, say, 2300 and 3800 Kelvin, depending on the pressure and the formulation. Condensed phase species are produced. This is in a propellant, especially if it's metallized, so if I add additional fuel in the form of different types of metals. The high temperature combustion products are mainly used for propulsion or gas generation purposes. And as I already mentioned, there's two types of solid propellants that are differentiated by the condition in which their ingredients are connected. Homogeneous, the oxidizer and fuel are chemically linked form a single chemical substance. These are physically homogeneous and heterogeneous, where the oxidizer and fuel are physically mixed but do not have chemical bonds between them. So these propellants are physically heterogeneous, and they're the more modern propellants today. What are some of the desirable characteristics of solid propellants? High gas temperature and a low molecular weight. For those who have had a rocket course, one of the important metrics is referred to as the specific impulse. The specific impulse is the thrust that's developed per unit weight flow of propellant. And what you find is this is proportional to the square root of the flame temperature divided by the molecular weight. So you can think of this in terms of an automobile, sort of like the gas mileage of your car. How efficiently do I use that propellant to get useful output? High density. If I'm working with a system that's volume limited, I want to basically have a high density energetic material. So another very important property in rocket motors today is what's referred to as the density impulse, where I take the product of the density times the specific impulse. And I do my metrics based on that then. A good mechanical and bond properties. One of the things that differentiates, again, explosives in propellants is an explosive, the mechanical properties aren't too important. Whereas in a propellant, the mechanical properties are very important. I need to make sure I know where the burning surface is all the time, okay? And under the G loading, say in a rocket or something like that, I can have a lot of strain. And that strain can actually start to de-wet the particles in the binder and create void spaces. And if I create cracks and things like that, I change the burning surface area, and I change all of a sudden then the burning output, the pressure in the vehicle in the motor changes, and I can have an overpressurization. So good mechanical and bond properties are important. Good aging properties. How's this solid material going to age over time? Desirable ignition characteristics, obviously low hazard manufacture and handling, predictable and reproducible properties, low thermal expansion coefficient, low temperature sensitivity, non-toxic exhaust gases with minimal smoke producing, low absorption of moisture, and minimum sensitivity of burning velocity to pressure, temperature, and gas velocity. Okay, where I may be looking at erosive burning. So if I'm looking at sensitivity of a material, typically I do that and I judge three factors. What is the impact sensitivity, where I might have an energetic material here, and I drop a weight on it. and I look at whether it'll ignite or not, okay? And it's a very simple experiment where I keep changing the height of the weight, okay? And I measure then the height of that distance when it falls on the material and when it ignites, okay? So that's impact sensitivity. I can also have what's referred to as friction sensitivity, okay, where something rubs over the surface of the energetic material. And there I look at the loading that causes ignition. And then the third measure of sensitivity is the electrostatic discharge sensitivity, where I might have a discharge of an electrical impulse to the material, whether or not it ignites or not. Okay, let's talk a little bit about homogeneous and heterogeneous propellants. Again, just some introductory material. Homogeneous propellants, uniform physical structure. Fuel and oxidizer are chemically bound. Major constituents are nitrocellulose and nitroglycerin. Nitrocellulose is a typical example of a homogeneous propellant, and it's nitrated cellulose whose chemical structure is represented typically between the two formulas I have here, overall formulas. Okay, and what differentiates them is the amount of nitrogen content. So if I were to buy nitrocellulose, typically I could buy it with either of those two loadings. And the higher the nitrogen content, the more oxygen and the more exothermic the system is. Propellants which are composed of nitrocellulose and nitroglycerin are called double-base propellants and are typical homogeneous propellants. Now, in the combustion community, we often deal with stoichiometry, air-to-fuel ratio, fuel-to-air ratio, and the energetics materials formulation. The formulators deal with something called an oxygen balance, okay? And they use this in formulating and adding different ingredients. So the oxygen balance is the amount of oxygen in weight percentage, which is liberated as a result of complete conversion of the energetic material to CO2, water, sulfur dioxide, aluminum oxide, etc. So I'm fully oxidizing all the elements in the material. In this case, the oxygen balance is a positive percentage, so I can write it in equation form as the oxygen balance is the mass of excess oxygen in 1 mole of a compound divided by the mass of 1 mole of that compound. Okay, if the oxygen is needed for complete combustion of the energetic material, then the oxygen balance is a negative percentage. Okay, and again, the oxygen or the calculation of oxygen balance is performed by assuming the conversion of the atom CHNO and aluminum into fully oxidized molecules, so all the carbon CO2, all the nitrogen to molecular nitrogen, all the hydrogen to water, and all the aluminum to aluminum oxide. And in the case of if chlorine's present, say in ammonia perchlorate, then I look at the conversion of H and Cl to hydrogen chloride as a reaction. So as an example, if I take RDX, which is a ring structure just like HMX, but instead of having 8 members, it only has 6 members in the ring, and it has an overall formula of C3H6O6N2, then since I have 3 carbons, I need to form 3 carbon dioxides. I have 6 hydrogens to form 3 water molecules, and 6 nitrogen to form 3 nitrogen. But if I look at the formula, I can see for complete combustion, 9 oxygen atoms are needed by taking those 3 reactions and adding up the total amount of oxygen. The substance itself only supplies 6 atoms, so that means there's 3 atoms are still required. And so if I look at the molecular weight of the 3 grams of oxygen atoms, which is 3 times 16, I get about 47 grams. And if I look at the total molecular weight of the RDX and take that ratio, I'll find that ratio ends up to be about 22%. Okay, but it's negative because I need to supply additional oxygen to complete all the elements to full oxidation. So the RDX would have a negative oxygen balance of 21%. So you might ask yourself, and I'll come back to this, why does one add RDX to a propellant? Since it's not going to supply it, and it's typically referred to as an oxidizer if that's done, but it doesn't supply oxygen to the mixture. Okay, well, if I look at what happens in RDX, this mixture will end up forming an equilibrium, something that looks like 3 CO, carbon monoxide molecules, 3 water, and 3 nitrogen. Now, what's the advantage of that? It actually becomes an ideal propellant because remember I said ISP is proportional to the temperature over the molecular weight. And so what I'm looking at is the trade-off of molecular weight by forming just CO instead of CO2 in the temperature that I yield. Okay? And so here I've decreased the molecular weight of the final product significantly to improve the specific impulse relative to the temperature because of dissociation of species at such high temperatures. Okay, so here's an example of the molecular structure of nitrocellulose. Okay, and you can see it's a repeating structure. The N here basically means that this structure repeats itself. And so you can see it consists of a ring structure of carbon, mainly some oxygen in the ring. And then off of the ring structure, cellulose has been nitrated. So basically these NO2 groups, nitrates, have been added to the rings. And that becomes the oxidizer for the carbon and hydrogen that's in the ring structure then. Okay, so this is an example of a nitration level of 14%, molecular weight of 297, oxygen balance of minus 24%. So again, doesn't have enough oxygen to fully oxidize the carbon and hydrogen. Density, very important, 1.66. Okay, if I look at something like a liquid hydrocarbon or even HTPB, the densities are going to be probably a little less than 1 gram per cc. So here you can see in this structure, I'm getting a higher density than I'd get out of something like a typical hydrocarbon fuel. Heat of combustion, 650 kilocalories per mole, enthalpy of formation, minus 156, and the physical state's a solid. If I compare that now to nitroglycerin, it has a structure shown here. So you can see it's a chain, linear chain of basically carbon with hydrogen off it, and off of the carbon atoms, I pulled off an H atom, and I put a nitrate group, an ONO2 group, on each of the carbons. Okay, without going into all the details, you can see it's a liquid versus a solid that the nitrocellulose was. So you'll see in terms of terminology later, the nitroglycerin acts as what we refer to as a plasticizer. Another example of a plasticizer to mix with, say, nitrocellulose is TMETN, which is nitromethyl-ethane trinitrate. And you can see it's again a CH structure in which I'm nitrating it with ONO2 groups. Again, it's a liquid, so as I said, it's typically used as a plasticizer added to the nitrocellulose to dissolve it and bake it into a gel that can be basically formed into grains. Okay, so let me just quickly say some comments about decomposition of nitrocellulose. And I'm going to talk about kinetics later on, but the way of looking at kinetics from a very simple point of view is looking at bond energies and looking at the weakest bond. What's going to break first, and then what are the initial fragments and how they're going to react. So when nitrocellulose is decomposed thermally, two major fragments are generated. One group of fragments with a CH or CHO structure acts as the fuel, with the other fragment basically being NO2. NO2 now is your oxidizer instead of molecular oxygen. Since nitrocellulose is a fibrous material, it's difficult to form a specified propellant grain using a single ingredient, again called a monopropellant. So liquid materials called plasticizers are usually mixed with the nitrocellulose to gelatinize it and to form a specific shape of a propellant grain. Typical examples of the plasticizers are the NG and TMETN that I just showed you. Both of them are also nitrated materials, which can individually function as propellants themselves. So if I go back here and I look at, say, the nitroglycerin, you can see it has a positive oxygen balance. So if I start adding it to nitrocellulose, I'm starting to change that overall oxygen balance of the mixture or the stoichiometry. I'm starting to bring it closer to a stoichiometric mixture. And if I look at the nitrocellulose, eventually, as I said, one might start asking, how's this going to initially react? Well, if you go through and you start looking at the weak bonds are going to be the ON O2 bonds. So when this initial, as I thermally heat it up, I'm going to break that ON bond. And off of it, then I'm going to get NO2. And then there's what's the next weakest bond after I remove that? It's basically a one removed bond that typically becomes the next weakest. So if I look at something like this bond breaks, okay, here's one. So the next bond that might break is this one removed. And once I do that, I open up the ring and I continually open it up, and eventually I form a lot of formaldehyde plus other aldehydes. And that NO2 then reacts with the formaldehyde and the aldehydes in the gas phase. Okay, so how about a heterogeneous composite propellant? It has a non-uniform physical structure. The fuel has a hydrocarbon structure. The most popular today is hydroxyl-terminated polybutadiene. The polybutadiene is referred to as the prepolymer, and it's just chain length is extended. The fuel has a dual function, basically to produce energy when burned with the oxidizer-rich species, and to bind the oxidizer particles together to form a specified propellant grain shape. The organic fuel material is initially in a liquid or semi-liquid form that can be cured to form a solid. Okay, and so the final product might look something like this, where I have a solid here, shown here, and in this particular case, I have oxidizer particles, and in this case, maybe they're ammonium perchlorate crystals of different size. So typically, I'll mix a distribution, at least a bimodal distribution, and sometimes a trimodal distribution. And that's for packing density characteristics. I want to get as high as solid loading of the oxidizer particles as I can. And so here would be the large particles and the small particles. And again, on the right here then is a micrograph of, say, an AP-HTPB grain. A little bit about how you might see their combustion shape. Composite propellants are usually made of a polymeric matrix loaded with a solid powder oxidizer and possibly a metal powder. Probably the most popular today is aluminum. Boron is also added, but it has some combustion difficulties. Okay, and these metals basically play the role of a secondary fuel component, and we'll talk about that later. The oxidizer and fuel-containing molecules come from separate components, and therefore the flame structure is three-dimensional and non-premixed. So if I go back and look at that structure I showed you on the previous page, and I draw it here, and I say, well, how's the flame structure might look immediately above the surface? What I might find is something like this. This out here is the fuel binder, and these large white pieces are, say, the oxidizer crystals, say ammonium perchlorate. And what happens is the ammonium perchlorate is often considered a monopropellant. It can decompose exothermically, like a premixed flame, because it has its own oxygen and a little bit of fuel components. So what will happen is right above the surface, I'll get like a little premixed flame. And out of that premixed flame, I'll generate molecular oxygen, about 23%, as I said. Now that molecular oxygen comes out, and this fuel over here that's holding the crystals together, because of the heat, starts to pyrolyze. And so off of the surface comes fragments of hydrocarbon molecules, butadiene, some different aldehydes. And so as they come up, they want to react with this excess oxygen that came from the ammonium perchlorate. And so they start mixing together. And one of the things they can do then is form a diffusion flame above the crystals. Okay. Now I kind of drew this in a large form here. You know, if I look at a real flame at pressure, this distance here at certain pressures, you know, might only be 100 microns or so. So it's very near the surface. So the major propellant properties such as burning rate, rheology, and mechanical behavior are directly dependent on the size and distribution of the fuel and oxidizer particles in the matrix. The oxidizer and metallic fuel ingredients are in the form of solid powders, which must be mixed with a binder to provide cohesion and distribution. The major types of ingredients in solid propellants, so I'm just going to go down and name some different types of ingredients in their main function without going into too much detail. Obviously, the oxidizers, usually crystalline particles to supply the oxygen-rich species. The fuel binders, typically liquid, from hydrocarbon polymers that holds the solid oxidizer particles together and provides the fuel-rich component. Also controls the mechanical properties. Plasticizers are used for obtaining superior characteristics of grain formation to improve the mechanical properties and to reduce shock sensitivities. Stabilizers are used for increasing the chemical stability of composite solid propellants. Then another ingredient I add is the curing agent or the cross-linking agent for curing the prepolymers in the binder material and forming chemical bonds between the binder materials. So the cross-linking agent basically helps to form the long chains in the complex three-dimensional polymers that end up being a solid and hold the matrix together. Some other ingredients that you'll find in solid propellants, and these are also found in explosives too. So a bonding agent is used to increase the adherence of each oxidizer particle to the binder. So I want to make sure that when this is being cured and formulated, there's no bubbles or void spaces between the binder and the oxidizer. That can actually introduce shock sensitivity characteristics if I have those voids. I can add a burning rate catalyst for increasing the burning rate of the solid propellants. Anti-aging agents can be added to use to avoid deterioration of the propellant physical properties with time. Opacifiers, this is more common in double-base propellants, are used to make the propellant less translucent to basically in-depth radiation absorption. If there's radiation, I want it to be absorbed at the surface. I don't want it to be absorbed very deep into the surface where it's going to cause too much reaction and start decomposing the material too early. Flame suppressants for basically suppressing the flame luminosity, and combustion instability suppressants for basically reducing the burning rate sensitivity to pressure fluctuations in the motor itself, say. So I put together, and I'm not going to go through each of these. These are some ingredients that you'll often find used in homogeneous propellants. And again, I list it by if it's a plasticizer in the form of a fuel or oxidizer or just a fuel, a binder, a stabilizer, a burning rate catalyst, a high energy additive, a coolant pacifier, a flame suppressant, a fuel, a metal fuel, or a combustion instability suppressant. And you can see, I've mentioned some of these already, the nitroglycerin, the metals, aluminum metal, in terms of the burning rate catalyst, and you'll find lithium fluoride or different stearates used. And I can make a list for heterogeneous propellants as well. So again, listing different types of oxidizers, binders, curing and cross-linking agents, bonding agents, plasticizers, burning rate catalysts, metal fuels, and again, combustion instability suppressants. So I'll show you some of these later, but these are still commonly used as different ingredients, and they have different advantages. So oxidizers, you can see ammonium nitrate, ammonium perchlorate, nitronium perchlorate, potassium perchlorate, the RDX and HMX, different types of binders. P-band was the binder that was used in the space shuttle rocket propellant. Today, you'll find it's been replaced with HTPB because of its higher energy density. Diisocyanates are typically used for curing and linking agents. They have some problems in terms of their toxicity. And list again burning rate catalysts. Here you'll find metal oxides and different types of metals. So you can look at that, and we'll talk a little bit more about that later. So again, some structures of explosives, just to get familiar with them. I'll just go through the top three here. TNT, you can see it's based on the benzene ring. Trinitrotoluene, so it's toluene. Toluene has one of the hydrogens removed and replaced with a methyl group, as shown here. And the trinitro means three of the hydrogens have been replaced with 3 nitro groups. Okay, RDX now is again a ring structure, but it's not based on the benzene ring. It only has single bonds between the components of the ring. And as I said before, these are carbon atoms, and off of the carbon atoms are 2 hydrogen. And off of each of the nitrogen atoms is your nitro group. HMX basically just extends this ring size from a 6-member ring to an 8-member ring. And the triamino, trinitrobenzene, again, is based on the benzene ring here. The amino groups are basically NH2 groups. Okay, so I have triamino, I have 3 of those on the ring structure, and trinitro, I have 3 of the NO2 groups. Okay, and you can look at the other ones independently. Okay, here's some properties of several solid oxidizers. So I list here, ammonium nitrate, ammonium perchlorate, hydrazine diperchlorate, hydrazine perchlorate, ADN, ammonium dinitromin, hydrominium nitroformate, nitryl perchlorate, RDX, and HMX. Important properties are melting temperatures, obviously their heats of formation, their densities. You can see the densities here are quite a bit higher than the hydrocarbon. So remember I said the typical binder HTPB is going to have a density like 0.9 grams per cc. So having a lot of oxidizer is going to be important to get the right equivalence ratio, but also increasing the density of the initial material. And you can see the oxygen balance. If I look at all the ones at the top, I'm going to be supplying oxygen to the formulation, and the 2 at the bottom, which are the high explosives, RDX and HMX, have a negative balance. And as I said, they're balanced almost perfectly for a solid propellant because they form CO, H2O, and nitrogen. Okay, I just want to finish this set of lectures with saying something about hazard classifications of solid propellants or explosives. How do you classify them? So the classification of the propellant, and the 2 that are important are 1.1 and 1.3, determines the method of labeling and the cost of shipping rocket propellants, loaded military missiles, explosives, or ammunition. It also determines the limits on the amount of propellant stored or manufactured in any one site and the minimum separation distance of that site to the next building. So if you remember, when I showed you our facility, I told you we have 2 magazines. One is rated for 1.3 material, the other is rated for 1.1. In each of those magazines, I can only put so much material. And they have to be a certain distance away from each other, okay? And so if I look at class 1.1, the propellants that can experience a transition from deflagration to detonation are considered more hazardous and are usually designated then as 1.1 type propellants. So with a class 1.1 propellant, a powerful detonation can sometimes occur, which rapidly gasifies all the remaining propellant and is much more powerful and destructive than the bursting of, say, a rocket motor case under high pressure. And I note here, unfortunately, the term explosion has been used to describe both the bursting of a case with its fragmentation of the motor and also the higher rate of energy release of a detonation, which leads to a very rapid and more energetic fragmentation of a rocket motor. One way to tell the difference between if I had a detonation or an explosion is really to look at the size of the fragments that are left over. If I find large pieces of fragments, it was an explosion. If I find that the pieces of the material are only little pieces, it detonated. Okay, in a class 1.3, most propellants will burn, and if they're in, I say, a rocket motor case, it may burst the chamber because the pressure gets high, but the propellant will not detonate. So 1.3 doesn't detonate. If the rocket motor case should burst violently, say with a class 1.3 propellant, then much of the remaining unburnt propellant would be thrown out, and then eventually it would stop burning because there's a lower pressure deflagration limit typically for many propellants, where if I'm at atmospheric pressure, they just won't burn. And then I also note there's 1.2 and 1.4 that really pertains more to, the 1.4 pertains to fire characteristics, no detonation, and the 1.2 corresponds to non-mass detonating and a fragment producing device. Okay, so a little bit over time, but let's take a break of the 10 or 15 minutes, what the typical time is, and then I'll come back and we'll look at the next set of notes. If you have any questions, and you know, come on up now, or ask them at the beginning of the next session so that they can be recorded.